All right, we're going to start chapter 5. Now we're getting into some actual chemistry. So, introduction to a chemical reaction. Chemical change or a chemical reaction converts one substance into another. Tell me how you know if a chemical reaction is occurring. What?
Heat.
Gives off heat. What else? Can't hear you.
Meat.
Smell. Gives off an odor. Possibly, yes. Anything else? Well, you can see it. You can see, if you mix two liquids, you see a solid forming. You can see bubbles. What about a glow stick?
What do
What do they give off?
Yeah. Light.
Light. May give off a sound, as in boom. You know, a chemical reaction occurred. So, a reaction involves breaking bonds in the reactants, what we call the starting materials, and forming new bonds in the product. So here we have methane and oxygen. We're going to pull all these bonds apart, essentially break them down into their atoms, then reassemble the atoms into new molecules, in this case, carbon dioxide and water. That's really all chemistry is. Take what we start with, break it apart, at least some of it, and then reassemble it in a different form. When we do that, the chemical reaction by the arrow there, there's usually a change in energy. We either give off energy, in the case of boom, or we absorb energy. And I don't know why we have a blank screen there, but... So, a chemical equation is an expression that uses chemical formulas and other symbols to illustrate what reactants constitute the starting materials in the reaction and what products are formed. So if we look at this equation at the bottom, the left side of the arrow, the methane and the oxygen, are the reactants. That's what we're starting with. The right side of the arrow tells us what we end up with, or the products, what we're producing. Coefficients, which are the numbers in front of the molecules. If you don't see one in front of methane, that means it's 1. Shows the number of molecules of a given element or compound that react or form. So we can think of it like a recipe. I like cooking examples because everybody can relate to cooking examples, baking examples. So if I say 1 cup of sugar, plus 2 cups of flour, gives us 3 cookies. Obviously, they're going to be big cookies. I kind of wrote a recipe in shorthand. Usually you get a cookbook, it has a list of ingredients, and it'll have a procedure say, okay, take 1 cup of sugar, add 2 eggs, beat it up, then add the flour, beat it up, and add baking soda, beat it up, then put it on a pan, put it in the oven. It's a whole procedure. But an equation would be take 1 cup of sugar, 2 cups of flour, you end up with 3 cookies. So the coefficients are really the amounts they react to. And you can think of the cups like moles. Remember we said moles or counting numbers? We did moles in here, didn't we?
Not yet.
Not yet. We will do moles.
We have joules and calories.
Joules and calories. So the law of conservation of mass states that atoms can't be created or destroyed in a chemical reaction. So whatever we start with, we have to end up with in terms of mass. If we start with 100 grams of starting material, we have to end up with 100 grams of product. Coefficients are used to balance an equation. You have to have the same number of atoms on each side. Okay? So if we look at this equation, methane plus oxygen gives us carbon dioxide and water. Count the atoms. If we look at the reactant side, we have 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. The coefficient multiplies everything in the molecule. So it's 2 times 2 is 4. Come over on this side. Carbon dioxide. This whole thing, we have 1 carbon atom, 4 hydrogen atoms, 2 times 2 is 4, and 4 oxygen atoms. We have 2 here and 2 here, because 2 times 1 is 2. So if you look at both sides, we have the same number of atoms. An equation has to be balanced. If it's not balanced, it's no good. You can't do anything. It's just like if I go back to our cooking recipe, if I say, well, how do you make cookies? Well, you take flour, and you add sugar, and you add baking soda, and you add eggs. Go do it. Well, then your response to me would be, how much flour? How much sugar? How much baking soda? You know, you can't say, well, I'm going to go in and put a cup of flour, 4 cups of sugar, 6 cups of baking soda, and expect to make a cookie. You just can't make up the proportions. So the coefficients are, you can think of them as the proportions. What else do we need to know? If I'm making cookies, okay, put the flour, the sugar, the eggs together, mix them up. To make a cookie or a cake or whatever I'm making, what do you have to do with that? Which means I'm heating it. Okay? That would be an important thing to tell you to do. Oh, I mixed them all together. There they are. They've been sitting there all day. I don't have cookies. Well, of course not, you dummy. You didn't put it in the oven. Okay. So, we have symbols we put in chemical equations. Okay, the arrow is the reaction arrow. That tells you what direction we're going. The little triangle means we're heating it. Then we have the states of matter, solid, liquid, gas. If you see AQ in parentheses, that means the stuff is dissolved in solution. If I say in a recipe, or you have NaCl, solid, that means you get your box of Morton salt and you add solid salt to it. If I say NaCl aqueous, that means the salt is dissolved in water. And you're going to add a salt solution. Balancing chemical equations. I took chemistry, especially in high school. They did it what they call the iterative method, which means trial and error. Certain equations, it could take you 40 minutes to figure out how to do it. I'm going to show you some shortcuts. Some of them are very easy, but hopefully this will help. We're going to start with, we're burning propane. My rule of thumb is I always leave hydrogen and oxygen to last. And if I have one of them by themselves, in this case oxygen, I leave that to the last of the last. That makes sense. So, what element will I start with? Which one's not hydrogen and which one's not?
Carbon.
Carbon. So we start with carbon. How many do I have on the left?
3,
How many do I have on the right?
0. Oh, 1.
One. If I had 0, then boy, it really be stuck. Okay. So to balance it, you can only add coefficients. You cannot add subscripts. Coefficients have to go at the front. They can't stick them in between molecules. They have to go in front of each molecule. So what do I have to put in front of CO2 to balance it? 3. So now I have 3 carbons on both sides. I'm going to go to hydrogen next. On the left, I have how many?
8.
On the right? 2. So what do I have to put in front of the water? 4. So now I have 8 hydrogens. So far, so good. How many oxygens on the left?
2.
How many on the right?
3.
Try again.
Oh, 6, 7. 7.
Is this an auction?
No,
6,
7,
7, 8, 9.
Seven.
Right here, 10.
All right. 7.
52.
Oh, no.
Okay. How many oxygens do I have in this? I have 3 times 2 here, which is what? 6. 4 times 1 is? 4. 6 and 4 is? 10. I have 10 oxygens on this side. Yeah, don't forget about this. So now I have 2 here. So what do I have to put in front of here? Give me 10.
5.
5. You gotta count all the atoms on each side. So now we're balanced. Next thing you do is
Can you go
check.
back one second? You said 3 times 2 is 6, and then 4 times 2.
No, 4 times 1. The oxygen is 1.
Okay.
You multiply by the subscripts only apply to the atom preceding it. So the 2 only applies to the hydrogen. The 1 applies to the oxygen. So now this is balanced. So that wasn't so hard. Let's try one a little different. Let's go up C4, H10, butane, same products. Okay, so what element we going to start with?
Carbon.
Carbon. That's not hydrogen and oxygen. On the left we have how many?
4.
So what I got to put in front of the CO2? What's the subscript with the carbon? 1.
Subscript. I'm sorry.
So I got to put what in front of the CO2? 4. Hydrogen. On the left we have 10. So what do I have to put in the one in front of the water?
5.
5. Wow, this is a piece of cake. Okay. We got 2 oxygens on the left. How many we got on the right?
Where? We have, 5. Plus 2 more. Plus 7. 7 of my time. 13.
13. 4 times 2 is 8. 5 times 1 is 5. 8 and 5 is 13.
Them subscripts leak. I'm going off, I tell you what.
So we have 13 oxygen on this side. We got 2 on this side. Here's that always used to screw me up, because now I got to go back and forth to figure out how to make those balance. Now I'm going to show you the shortcut. What is 13 divided by 2? 6.5. So I'm going to put a 6.5 here. You can't have a 6.5 in an equation. I mean, it balances, but you can't have 6.5 or something. So I got to make that a whole number. How can I make that a whole number? You can't round. No. What about if I multiply it by 2? Then 6.5 becomes 13. Okay. But if I multiply that by 2, I have to multiply everything in the equation by 2. So I'm going to multiply everything by 2. So now I have 2 times just the coefficients, 2C4H10 plus 2 times 6.5, 13O2 goes to 8CO2 plus 10H2O. So, check this. How many carbon on this side? 8. How many here? 8. How many hydrogen? 20. 20. How many oxygen? 26. Here we have 16 here, and 10 here. 16 and 10 is 26. So that's the balanced equation. If you want to do this equation, if you were going to the lab to do it, you have to have 2 molecules of butane react with 13 molecules of oxygen, and you'll end up with 8 molecules of carbon dioxide and 10 molecules of water. So just to illustrate this, if I said, we're going to make water. Hydrogen plus oxygen gives us water. Everybody knows this. You have to remember hydrogen and oxygen are diatomic. So, okay. Here's hydrogen plus oxygen gives us water. That was simple. I take 1 hydrogen molecule, 1 oxygen molecule, and I get 1 water molecule. No, it's not balanced. What do I have to put where? 2 in front of what? Here or here? So I put a 2 here, so now the oxygen's balanced. Now the hydrogens don't, so what do I have to do? Put a 2 here. So now it's balanced. What this tells me, if I want to make water, I have to take 2 molecules of hydrogen, 1 molecule of oxygen, and get 2 molecules of water. I cannot put it together to give me 1 molecule of water. Okay. Let's try a couple of these, because it's important that you learn to balance equations. You're going to be given word problems, and you have to write the equation. Does anybody know what this is equation for? Well, that's glucose plus oxygen goes to carbon dioxide and water. Anybody know? A&T people? What? I can't hear you. No.
It's the thing that happens with the gas and carbon exchange. Carbon.
We're taking glucose, and what are we doing to it? Take carbon dioxide and water. It's part of metabolism. Glycolysis?
Ooh, yeah.
Oh, yeah, glycolysis. Probably wasn't presented to you in terms of chemistry, but that's glycolysis. Okay, let's balance this. Go ahead.
So, are you adding hydrogen in that situation? Is that more of like a, you're talking an added?
We're not adding anything. We're breaking it down.
Okay.
So go ahead and balance it. Okay. Once again, start off with the carbons. We need a 6 here. Then the hydrogens.
Hold on, how do you get the 6 right there?
6 carbons.
Isn't that one carbon right there?
Yeah, if you make them balance, you gotta put a 6 in the front.
So because my confusion is I'm thinking if there's 1, you only need 5.
No, it's this times whatever the coefficient is. Subscript. So it's 6 times 1, 6. So I have 12 hydrogens here, so I have to put a 6 here. 6 times 2 is 12. So now over here, how many oxygens I have? 18. Okay, I don't want to touch this, so I subtract 6 from the 18, which gives me 12. So can I put some coefficient in front of here to make this 12? 6. 6 times 2 is 12. So now everything balances. 6 carbons, 12 hydrogens, 6 oxygen and 12 oxygen are 18. 12 oxygen and 6 oxygen are 18. Let's see if we can get another one here.
Can you count the oxygen again for me? Because I got everything up to the 6.
There's 6 in here.
Uh-huh.
And 6 times 2 is 12. That's 18.
Oh, no, I was just adding.
And 6 times 2 here is 12. And 6 times 1 is 6. And 12 and 6 is 18.
I think I added it.
Okay, balance that one.
And then on the other side.
Yeah, that's an Na. Another trick is if you have a polyatomic ion that's the same on both sides, in this case we have SO4 on both sides, treat it as one unit, just balance all the SO4s. You don't really have to count those oxygens. Sorry. We start with the NAs, it goes really fast. So if I start with the NAs, what do I need to do? I need to put a 2 in front of the sodium hydroxide. Okay, we got one SO4 on both sides, so that's fine. How many hydrogens we got on the left? 3. Try again.
Oh, now we got 5.
Try again.
4.
4. 2 here, 2 here. That's 4. So what do I need to put in front of the
H2O4.
2? So now we're going to count oxygens that aren't part of the SO4. So how many do we have here? 2. How many do we have here? 2. So we're done.
How did you get that on the left side of my I mean,
We have a 2 here.
not that. You said there was 2 oxygens on the left?
2 times 1. We're not counting SO4s.
Okay.
2 times 1 is 2. Because there's a subscript of 1 for the oxygen. So again, practice these. Web link page has a whole bunch of them that you can practice. again, it's important that you learn how to do this. The next step. There's always a next step. Okay. That just goes through what we did for propane. Oxygens, okay. You want to always check at the end that you have the smallest set of whole numbers. So if you can reduce the equation, reduce it. Just the coefficients. So if you came up with 2, 10, 6, and 8, you'd have to reduce it to 1, 5, 3, and 4. So here they're going to talk about the chemistry of an automobile airbag. Inside your airbag is a compound called sodium azide, which is explosive. And you have little sensors in your bumper, so if you hit the bumper at a certain speed, it sends an electrical impulse to the sodium azide, and it explodes. This is the reaction. Gives you sodium and nitrogen. The nitrogen is what fills up the airbag. 40 milliseconds, so it's like, boom, bag pops out. And then hopefully it deflates again. And now they try to tell you when you drive, keep your hands at 4 and 7 rather than it used to be 10 and 2. And with 10 and 2, the airbag goes off, it tends to knock your hands back into your face if people injured themselves by hitting themselves in the face, essentially.
Takes a lot of skin off your forearms, too.
Speaking from experience?
Yeah.
Oh. Don't drive with him. Okay.
Takes the skin off your forearms.
We're going to introduce a new term, the mole. Avogadro's number. A mole is not a furry little animal in chemistry. A mole is a quantity that contains 6.02 times 10 to the 23rd items. It is a counting unit. No more, no less. If I said, bring me a dozen eggs, how many eggs are you going to bring me? 12. A dozen oranges, you're going to bring me 12. So a dozen means 12. A mole means 6.02 times 10 to the 23rd. So 1 mole of carbon atoms is 6.02 times 10 to the 23rd carbon atoms. A mole of water molecules is 6.02 times 10 to the 23rd water molecules. A mole of vitamin C molecules is 6.02 times 10 to the 23rd vitamin C molecules. 6.02 times 10 to the 23rd oranges is how many oranges? 1 mole. Thank you. Just like 12 eggs is 1 dozen. And 6.02 times 10 to the 23rd anything is 1 mole of that. So 6.02 times 10 to the 23rd cars is 1 mole. 6.02 times 10 to the 23rd avocados is 1 mole. Since they're avocados, that's a quacamole. Okay. So again, we can use conversion factors. We have an equality. 1 mole is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd is Avogadro's number. That's the number you need to remember or write down. Or when I say Avogadro's number, that's the number I'm talking about. So how many molecules are contained in 5 moles of carbon dioxide? Well, we're going to do a conversion. Five moles of CO2 is what we're that's a CO2. We want to know molecules. So you're going to have mole here on the bottom. So 1 mole of CO2 contains how many molecules? 6.02 times 10 to the 23rd. So I'm going to take the 5 and multiply it by the 6.02 times 10 to the 23rd. 30.1 times 10 to the 23rd, which is 3.01 times 10 to the 24th. So that's how many molecules you have in 5 moles.
What does that say molecule on top of there?
CO2. Just like if I said, bring me 5 dozen eggs, you would know to bring me 60 eggs. So, that's all it is. Okay? So you should be able to go from moles to, we're going to call them particles. They could be either atoms, molecules, and go back. We need to know a formula weight. Formula weight is the sum of the atomic weights of all atoms in a compound, reported in atomic mass units, AMU. So what is the molar mass? This is another term for formula weight of nicotine, C10H14N2. To figure that out, well, we know we got 10 carbon atoms, 14 hydrogen, 2 nitrogen. We just look up on our periodic table. Carbon is 12.01. Hydrogen is 1.008. Nitrogen is 14.01. So it's 10 times 12.01. 14 times 1.008. 2 times 14. Then you add them all up. So the formula weight of nicotine is 162.23 AMU. And when you do these problems, please be sure to use the periodic table in your book. If you picked up a periodic table from somewhere else, some of them are more exact, they have like 4 or 5 decimal places, you may get a rounding error when you do the calculations. Okay? So if I give you any molecular formula, or any compound formula, you should be able to tell me its molar mass. Well, the formula weight is in AMU, so we're talking about adding up all the atoms. Molar mass, because you can't go in the lab and weigh out atoms. The molar mass is the grams. So if you look at the carbon's atomic weight is 12.01 AMU. Its molar mass is 12.01 grams per mole. So if I took 1 mole of carbon atoms, 6.02 times 10 to the 23rd carbon atoms, it would weigh 12.01 grams. So if I ask you what the molar mass of any element is, it's the same as the AMU. So if I ask you what the molar mass of nicotine was, I forgot what it was back there, 162 something. Its formula weight is 162 AMU. Its molar mass is 162 grams. It's the same number. We're talking about atoms, we're talking about AMU. If we're talking about molar mass, we're talking about grams. Okay. How many moles are present in 100 grams of aspirin with a molar mass of 182 grams per mole? So what do we know for sure? What are we starting with? 100 grams of aspirin. And it's 100 points, that's 3 significant figures. What am I looking for? Moles. How many moles? Eventually I want to end up with moles. Abbreviation for moles is MOL. So I have to have a conversion factor. It's going to have one on top and one on bottom in terms of units.
Hands on the bottom.
Grams on the bottom. What on the top? Moles. Okay. So, 1 mole of aspirin weighs how much? 180.2 grams. So it's given right here. So now you just do your plug and chug. 100 divided by 180.2 will give you the number of moles. 0.555 moles of aspirin. Okay? Again, it's an easy conversion. Going back to, let me get rid of this stuff I put here. The balanced chemical equation tells us the number of moles of each reactant that combine and the number of moles of each product formed. That's what the coefficients tell us. 1 mole of nitrogen reacts with 1 mole of oxygen to give us 2 moles of nitrogen monoxide. Chemicals react in moles, not grams. Normally you wouldn't put the ones in there, they would be understood. So we can look at conversion factors. They're really just ratios. So if I start with 1 mole of nitrogen, how does the nitrogen and oxygen react? 1 to 1. For every nitrogen, how many nitrogen monoxides I get? For every 1 nitrogen, I get 2 nitrogen monoxides. For every 1 mole of oxygen, I get 2 molecules of nitrogen monoxide. So if I wanted to get 4 moles of this, how many would I have to start with here? 2. If 1 gives me 2, 2 gives me 4. 4 give me 8. So to go moles of A to moles of B, we can use a mole-mole conversion factor. Now, I'm going to give you the stoichiometry roadmap. I think I posted it on Blackboard. This is one you can write down. I'll give you a chance to write this one down. Stoichiometry roadmap. I believe that's on the Blackboard under this chapter. If not, I'll put it on there. But it tells you how to do everything we're going to do. And it is literally a roadmap. Let's try using this roadmap. Here we have an equation. We're burning ethane. And I had to correct it because they had the wrong number of carbon monoxide molecules in there. The key to using the roadmap is knowing where to start and where to end. So you got to read the problem. How many moles of carbon dioxide are produced from 3.5 moles of ethane? So what do we know in this problem? 3.5 moles of ethane. We're going to call ethane A. That's the first thing we're going to see. So we're just going to call it A. All right? So we're starting here, moles of A. What are we looking for? How many moles of CO? Now, CO is different from ethane, so CO is going to be B. So we want moles of B. So this is where we're going to end, over here. I can't because I got a split screen. So if I go from moles of A to moles of B, what does it say to use? Coefficients. So I have 3.5 moles of C2H6. Ultimately, I want to get to moles of CO. If I follow the street, I can go from moles of A to moles of B. It's just one arrow. So moles of B would be moles of CO. I came from moles of A, so that would be moles of C2H6. It says use the coefficient. So I look at the equation. What's the coefficient in front of CO? 4. So I would put a 4 there. What's the coefficient in front of ethane? 2. Now I got everything filled in. What's the answer? Don't use your calculator. 7. 4 divided by 2 is 2. 2 times 3.5 is 7. So if I start with 3.5 moles of ethane, I end up with 7 moles of carbon monoxide. Yes? No? Okay. Unfortunately, I can't bring that other one back in, but there's the answer. Here we have and I'm just going to stop this a second. All right, let's go to this problem, making ozone from sunlight. What do we know for sure? What information are we given? Of O2. So we're going to call that moles of A. It's the first compound we're looking at. We're going to call it A. We have two choices, A and B. Doesn't really matter which one you choose, but I always choose A. So we're starting here. What am I looking for? Grams of O3. O3 is different from O2, so O3 must be, it's not A, it must be B. So I'm going to end down here. Grams of B. How many roads do I have to go down? here, that's 1. From here to here, that's 2. So if I'm going to write this, it would be 9.0 moles of O2. What's our next stop? You go from moles of A to moles of B. Right? That's the next little station here, moles of B. So B is O3, so we go here. That's on top, that's where we're going. We came from moles of O2. Then from moles of B we go to, what's the next stop? We're going, where are we ending? Grams of B. Grams of O3, where we've been was moles of O3. And we end up with grams of O3. Look at this. This cancels, and we're left with grams. So when we go from moles to moles, we use what, according to the map? What's it say? Coefficients. What's the coefficient in front of O3? What's the coefficient in front of O2? 3. When we go from moles of O3 to grams of O3, we're going from moles of B to grams of B. What does it say to do? It's written right there. What does it say to do? Read it. By what? Molar mass. So 1 mole of O3 is how many grams? Oxygen 16. 16 times 3 is 48. We got it all done now. It's just plug and chug. Five, 32, 284.
284, 288. Minus 3 from 9 is 3 times 2 is 6 times 48. 6 times 48 should be 288.
288. And they rounded up two significant figures to 290.
Can you do one more?
Oh, we're going to do plenty of it. If you know where you're starting and where you're ending, the road map tells you what to do each step of the way. Think of it as a GPS for stoichiometry.
So you did 9.0 times 2 divided by 3.
Well, I did 9 divided by 3 times 2. 9 divided by 3 is 3. 3 times 2 is 6. 6 times 48 is 288. All right. Bless you. Let's do this one. Ethanol, there's its molar mass, is synthesized by reacting ethylene with water. How many grams of ethanol are formed from 14 grams of ethylene? So what are we starting with? Grams of what? No.
Oh.
So what? Still in.
More than that.
No, we are starting off with what? Look at the problem. Grams of ethylene. So that's grams of A. So we're going to start here. What do we want to know? Grams of ethanol. So we want to know grams of B. How many steps do we have to take? 1, 2, 3. According to our map. So 14 grams of ethylene. Where do we go from grams of A? What's our next stop? What's the next stop? Sir, what? Mole of A. Where we came from goes on the bottom. Now we're at mole of A. What's our next stop? Mole of B. Don't read that. Well, don't read what's on the line. Read the stop. Those are in between the lines. Moles of ethanol. Where we came from, moles of C2H4. What's our final stop? Grams of B, so it's grams of ethanol. Over moles of ethanol. If you look at this, just the units, the moles of ethanol cancel, the moles of ethylene cancel, the grams of ethylene cancel. Now let's put in the numbers. 1 mole of ethylene weighs how much? What's its molar mass? 28.05. Moles to moles, what do we use? Now, coefficients. So what's the coefficient in front of ethanol? What's the number you see here? 1. What's the coefficient in front of ethylene? 1. For the last one, 1 mole of ethanol weighs how much? Hell! Molar mass of ethanol, it says right here. 46.07.
Wait to stop fast. Let me finish.
All right, now you do the calculation. So we have 14 times 46.07 divided by 28.05, 22.99. And they want 2 significant figures. 23 grams. Okay. Yes, no, maybe, don't have a clue. The map tells you what to do every step of the way. Where you're going to. These are the stops in between the lines. The lines tell you what to do. So you go from one stop to the other, the next stop goes on top, where you've been goes on bottom. So when you get to the end, everything cancels out but that last stop, which is what you want. Okay. Let me see what goes next. Stop for a minute. Okay, we're going to stop for a minute.